Hey everyone, welcome to the first lecture of the school year, and today we're going to be learning about vectors and scalars. Now these are things that we're going to be dealing with throughout the entire year, so it's good to fully understand them, and we're going to make a good step in that direction today. What I want to emphasize to you is that we make a difference between vectors and scalars because we have in physics what we call a frame of reference, and we use that very often. We'll explain that as we go along, especially in this topic, topic 2. We'll talk about frame of reference and how that applies, how that may change some things that the way you observe things, the way you record things, the way you measure things. So let's dive right in and start on this topic. All right, so first thing I want to talk about is the difference between vector and scalar. Now, some of you may have covered this in math already, and you may understand this to a lot more detail than what I'm going to go into, but I'm going to give us the detail that we need for this physics class. Now then, the first thing to understand is what the difference between vectors and scalars are. Okay, so a scalar, let me get the right color here. All right, so a scalar, why am I, let's see here. There we go. All right, there we go. Not sure what was going on there, but now we've got it. Okay, so scalar is basically just the magnitude of a measurement. Okay, magnitude, basically the number. Okay, it's if I am measuring something and it's 45 pounds, 45 pounds is the magnitude of it. Now a vector is magnitude with a direction. So I could measure something. Let's say I measure a football field and find that it's 100 yards. Well, the 100 yards is the magnitude. And if I measured it in the direction, say going north, 100 yards north, that makes it a vector. So think of a vector as something with an arrow attached showing what direction it's going. We don't always use an arrow. We may use plus or minus signs. We use basically the words north, south, east, west, up, down, in, out, any of those kind of words to indicate direction. But mostly we use arrows and we use plus or minus. Now, just to give you an idea, let me draw a little thing here, north, south, east, west. Generally, when we're talking about directions, north and east are given positive signs, south and west are given negative signs. Up is given a positive sign, down is given a negative sign. Let's see, in is positive, out is negative. This is just for your reference so that you, when you're talking about something, the rocket had a velocity as it lifted off of 1,000 kilometers per hour. You know it's going up, so that 1,000 kilometers an hour is a positive. Now the capsule, after orbiting the Earth, came back down, and it was averaging 20 kilometers per hour as it came down under its parachutes, so that would be a negative 20 kilometers per hour because it's going down. So just keep that in mind. Okay, so there are things. This topic is called motion. There's all kinds of motion involved, and we're going to spend quite a long time on the part of motion called mechanics. Now, mechanics is breaking motion up into its pieces. When you are throwing a ball, you throw it kind of up and in a vertical manner and in a horizontal manner, so it will go away from you, right? So like, say you're playing catch with somebody, you kind of throw it up in a parabolic way so that it makes it to the other person and they can catch it. So we break that motion up into those different kinds of concepts. We use vectors to describe that, and we use magnitude to describe how we measure it. So here's a for instance. We have, let me get this, we have a thing called distance. Distance is a quantity that tells us how far something has gone. We usually measure it in meters, and that's abbreviated M. We also measure things by how fast they go over time. So we have speed. That's usually in meters per second. And that's given us as m s to the minus 1. Remember math, minus 1 means it's on the bottom of it's in the denominator of a fraction. So we write it this way. This is the convention of IB, and it makes a lot of sense when we're talking about dealing with units and canceling units out and things like that. So it actually makes things easier once you get used to that. We also have a unit called time. And time, of course, is usually measured in seconds. Of course, it could be minutes or hours or things, but I'm giving you the base units for all of these. It could be kilometers, it could be kilometers per hour, or whatever. It's seconds, and that's abbreviated S. These are all scalar quantities. So I'm going to write these down. Distance, speed, and time. These are the main scalar quantities that we use to describe motion. We have others that we use to describe motion as vectors, things with a direction. One is called displacement. And again, that's in meters, abbreviated M. Velocity is in meters per second, just like up here. And then time is not, there is no vector for time. Time only moves in one direction. Time only goes in the positive direction. There is no negative time. So we treat it as a scalar because basically there is no direction, that it only goes one way. So the other thing we have is acceleration, and I will, over the course of time, explain what all of these are and how we deal with them and how we work with them. All right, so acceleration is in meters per second squared, and I will talk about what that per second squared means when we get to it. But right now, just understand that's what the units are, and it's a scalar. It has a direction. So let me write these up here. So not every, but these scalars have an equivalent vector. In other words, displacement is distance with a direction. Velocity is speed with a direction. And then there's acceleration, which is not part of time, but it is the vector that we need to use to describe how velocity changes. We don't have a scalar for acceleration because when you think about acceleration, two phrases come to mind: speeding up and slowing down. Just by saying speeding up and slowing down, you're giving direction to that. And so you're not talking about a scalar, you're talking about a vector. So speed is a scalar, velocity is a vector, acceleration can only be a vector, time can only be a scalar. Okay, so I've got that covered, and we'll talk more about what all of these are, especially as we get into this. I'm going to bring up a map here. This is a map of Austin, and I've asked Google to show me how to get from the Texas State Capitol up to Westwood High School. It's labeled here work. Google knows that I work at Westwood High School, so that's where that is. And it gave me a couple of choices to take to get up there. And it gave me, it's very circuitous, it's not straight, there's no straight path there. I've got to take all of these different roads, and it gave me a distance of 28 kilometers. Distance. And I call this a distance, 28 kilometers, because I'm not really, even though on the map you can tell you're going from south to north, the distance is really not there to tell us what direction we're going. It's just telling us how far we have to go. We look at the map to figure out how far we have to go. So the 28 kilometers, if I was going to figure out gas, I've not done this before, or I go visit family in states way north of here and I'm driving, I have to calculate how much gas I'm going to consume so I know how much money to bring and spend on gas. So all I need to know is the distance that I'm going to travel. Okay, so that's pretty easy right there. It's 28 kilometers. We'll go with this main one that they suggest. 28 kilometers is how far it says that we need to go to get to work, my work up here. Now I'm going to bring up another thing here, another map. Same map, only I've added a straight line. As old farmers in my rural days when I lived on farms and things like that, they would say as the crow flies, meaning a straight line. Obviously roads do not always go in a straight line, but if you went in a straight line, you would see that we are actually 21 kilometers away from the state capitol. Now I'm going to do this. This is distance. You can always do that. I got to get in the right layer here. All right, distance is 28 kilometers. I'm going to say the displacement is 21 kilometers. It's close to 20.91. That's close enough. We'll round it up to 21 kilometers. So by going this crooked all around route up here, we add 7 kilometers to our trip rather than going straight. But because of terrain and things, obviously we cannot go straight. Now what is going on here? The distance tells us how far we're actually traveling. The displacement tells us how far away we ended up from where we started. Okay, so there's two things in it, and it's vitally important because you'll want to know how far we are displaced from where we began. You'll also want to know how far we had to go to get there. And also we have a time here. So we have time equals 21 minutes to go this 28 kilometers. So you've probably seen this before. Speed equals distance over time. So I'm going to calculate this out, and it's 21 minutes. Why did I put minutes up there? Time. The speed is 28 kilometers over 21 minutes. And so it's 1.33 kilometers per minute. Whenever you hear per, that's that divisor, right, in the fraction, and so that means that you have every minute, every 21 minutes you go 28 kilometers, or in this case every minute you go 1.33 kilometers. All right, so that's calculating the speed. We didn't really care about the direction, but if you look at the displacement over here, we go 20, this displacement, we're going to be calculating velocity, because velocity is a vector, displacement is a vector, and time is not. Now, even though time is not a vector, it's a scalar, because we have a vector in the equation, that makes the answer a vector. We need a direction for that as well. Let's say it takes the same amount of time to go from the capital there using our route. Well, that would mean we go 21 kilometers in 21 minutes. And so our velocity is 1 kilometer per minute. But we're missing something. This is a vector, so we need a direction, and we can do this one of two ways. It's positive. We make it a positive, meaning we end up north of the capital, or we could say 1.0 kilometers, and it's really not straight north. It's kind of northwest, 1.0 kilometers, 1.0 kilometers per minute to the northwest. All right. Now then, I want to show you something else about vectors here. We set everything up. Let me put it over here. We set everything up on the XY axis when we're doing our problems. Everything is going to be in the XY axis. And we're going to do a lot of graphs in my next video. But looking down here, well, let's see, let's look at this one first. Let's draw a line from here down. Try to get that as straight north and south as we possibly can. And then draw one over to here. And make these vectors. Now, to go this direction, it's as if we drove straight line, we drove straight west for a little bit, and then straight north for a little bit, we'd end up right at Westwood. So what this is, and those of you that are familiar with vectors understand, this is a vector because it's a direction to the northwest. And it has component vectors. It has an x component and a y component. And if we add these components up, meaning we take the x component and we add the y component to it, we're going to get, we're going to get the resultant vector. Sorry, not drawing very straight here. Not sure what's going on here with my hand, but it's just not drawn straight. Okay, but we get this vector, this resultant vector. So these are component vectors, and this is a resultant vector. All of this is very important information. You're going to need to understand these key words. That's a component, and that's a component. And that's a component of these. Now, the interesting thing is, if I did these backwards, if I went north first, and then I went the same amount west that I did in this one, I would still get the same resultant vector. Okay, just that can be important when we're dealing with trying to figure out resultant vectors and so forth. Okay, the same thing happens over here. If we make a vector of all the different directions and can find the components of each of those, so let me give you an example. We basically have a vector right here that looks like this. There's an x component and a y component. There's another vector here. I drew it too far. It's to here. And there's an x component and a y component. There's one here that has an x component, y component, x component, y component. One here, which is different, it has a x component in the negative direction, y component. This one has one in the negative direction for the x component, y component. And we go on and on and on. If we add all of these up, if we add all the x components up, it's going to equal this one. If we add all the y components up, it's going to equal this one. Okay, so they're all going to eventually work out to get us to the same point. It doesn't matter how many of these there are, all of the y components. Now, in this case, notice that we have some going in the positive direction and we have some going in the negative direction. So they will add up, add up, add up, subtract, subtract, add, subtract, add, subtract, until we get up here and we have the negative x component. This is actually negative x, and this is positive y. And all of the y's are positive, so we will end up being up north, like this says. So we will be adding and subtracting. You know, they're adding, they're positive, positive over here, but then there's many more negative ones, and so eventually you cross the origin here and you go negative, and you get the negative value of the x component here. Now, that may or may not be clear to you at this point. We're going to be doing a lot with this, and you'll understand it very thoroughly here fairly soon. Okay, so the main thing to take from this is that the displacement is the distance. Now I want to say how far, not the distance, because that's scalar. The displacement is how far you end up in a straight line from where you started out. The the distance is how far it took you to get there, right? If you have to go from position X to position Y, and you have to go over a mountain to get there, you're going to walk a lot farther this way than you're going to end up this way. But this is your displacement, and this is your distance, okay? And the displacement has to have a direction associated with it, one way or the other. Okay, so hopefully that is clear. All right, I want to do one more thing. I want to talk about how we add vectors up and work these things out. Let me make a couple of little adjustments here. All right, this is Caraway Elementary School. This is where my daughter went, and we didn't live where I'm going to say we do, but we'll pretend like we lived right. I keep forgetting to indicate to the program where I am. Okay. All right, we're going to say we lived right there. All right, and every morning my daughter would walk to Caraway. So she would walk south, and then she would walk south 1 block. South 1 block. Then she would walk east 1, 2, 3 blocks. All right, so she would have gone a distance of 4 blocks, right? But she has a displacement of this. Now, this is a right triangle, so what do we use to figure out what this distance is? We use Pythagorean's theorem. A squared plus b squared equals c squared. So a squared is 1 squared. B squared is 3 squared equals c squared. So c squared equals 10. C equals the square root of 10. And in physics, we do not leave this as a square root. That does not tell us anything. We can't work with that. We have to convert this to the decimal number. So we just work this out. We enter this into our calculator, and we find out that the square root of this is 3.2. Oops. I am having a hard time with my pen today. 3.2 blocks from where she started. That is her displacement. 3.2 blocks east, we'll say. Okay. Now, let me go further now. Okay, she stayed at school for a while. She, spent her day there, and then she's going to walk back home. So she comes back. She goes west 3 blocks, right? 1, 2, 3, and then she goes north 1 block. But she's going to a friend's house, which is about 2 more blocks west. So she goes west 2 more blocks. Now, in this case, she has gone 3, 4, 6 blocks. And her displacement from where she started, and this is where frame of reference comes in handy. She either started here, or this morning she started here. So if she is starting from where she started this morning, she is minus 2 blocks because she's west. If this is the positive direction, she has passed where her origin was, and she's gone in the other direction, and it's negative 2 blocks. Or she's going to have to do Pythagorean's theorem to figure out what that hypotenuse is, to find out what her displacement from where she started at Caraway is. Now that's breaking this up. This was the morning. This was the afternoon. For the whole day, she went 4 and 6. She went 10 blocks. Her distance was 10 blocks. Now, at the end of the day, she's got to go home, right? So she comes home. What is her total displacement at the end of the day? It's 0 blocks. She didn't go anywhere as far as physics is concerned because she's right back where she started. However, her distance is no longer 10 blocks, it's 12 blocks because she went those two additional blocks to get home. Okay, so that is how we use scalars and vectors, and using distance and displacement, figuring out how to describe things. And it's important. It does make a difference, because if you're keeping track of your steps for the day, your distance that you travel is very important. But if you're just wondering, how far did I end up from where I started, displacement is very important. And when you're calculating velocity versus speed, you have to use that displacement. All right, the last thing I want to show you is I want to set up and show you a little bit of graphing. All right, so what I'm going to do is I'm going to set up a graph here. on this graph, I'm going to put x distance and minus x, and this is going to be time, so over time. And I'm going to describe this motion, her motion all through the day. I'm going to describe it on this graph. And we're gonna make this, don't have it drawn too well, 1, 2, 3, 4 blocks. 1, 2, 3, 4, but these are all negative, and this is 0. This is her origin, this is home. That's where we set up where the origin is home. So starting out, the first thing she did was she moved south. She went -1 block. And then she went positive for 3 blocks. 1, 2, 3. And then she stayed at school for a very long time, right? It's too long, I don't want to sit there. She stayed there for like 6, 7 hours, did her thing, was a really good student, right? And then she went home. So she went backwards. She went to the east, 1, 2, 3 blocks. And then she went north 1 block. All right, so she went, I'm sorry, I think I said east. She went west 3 blocks, so she went west is in the negative direction. And this is sloped because she did it over time. She didn't instantaneously appear there. It took her some time to get there, right? So this is a slope. And you'll notice that for the most part here's a positive slope because she was going in the positive direction. Here's a negative slope because she was going in a negative direction. And here's no slope because as far as we're concerned, she was at school. She was not moving from that spot. All right, so she went negative, she went positive, and then she went negative again. She went to the west and she went negative for two more blocks. And then she went 2 blocks and ended up back at the origin over time. So that is how you describe motion using a graph. Most graphs will not be this complicated, but you will see graphs like this that you'll have to figure out what is going on. And we'll also have, this is called a displacement versus time. We'll also have velocity versus time, and we'll have acceleration versus time, which we'll talk about next time.